Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss about the dot product. So this is one of the ways how we can multiply the two vectors. And also we're going to use how we can use the information about the multiplication of these two vectors in order to find the angles between the two vectors. Well, the dot product of two vectors which are given with the two tuples, three tuples, or in general with n tuples is a scalar. It's a number which is going to be obtained in the following way. So we are going to multiply the corresponding components of the vectors. The first component was the first component, second component was the second component, the third component was the third component of the two vectors, and then we're going to sum them up. So at the end, we are going to denote the dot product as the dot, simply u dot v is going to be equal to the u1 times the v1 plus u2 times the v2 plus u3 times the v3. Well, one of the easy ways to see the examples of the dot product in computer science would be the storage of the two vectors and doing some operations with them using the loops, for example. So let's assume that you know the data on the number of the sold ice creams of some small store. So in May, there were 15 ice creams sold. In June, 20, and July, 25 ice cream have been sold. So you can create one vector. Let's say u is going to be equal to the 20, so 15, 20, and 25. And at the same time, the price for the ice cream was different on those months. Essentially, in the first month, in May, it was $5 per ice cream. In the second month, it was $4. In the third month, it was $3. So you can create another vector to store the price for those vectors, for those prices. As well, it is going to be $5, $4, and $3. So now if I say what is the revenue of the store which sells the ice cream, is essentially how much money they've got at the end. What you need to do is you need to know that in the first month they've sold 15 ice creams per $5. In the second month they sold 20 ice creams per $4. In the third month they sold 25 ice creams per $3. So in total they've got this amount of money as in revenue. And you can see here that this is nothing else as the multiplication of the u to the v. Well, obviously, if you just got 3 months, it is not really useful to use the dot product, but you can imagine that your computer is going to have a vector, is going to have a data array with millions of data points, and then whenever you need to find a revenue, you can just do the dot product instead of creating the loop, multiplying every element of the first array to the second array, and do the summation. So this is one of the elegant ways to obtain this kind of information from the two vectors. Well, today mostly we're going to discuss about the geometric perspective, geometric applications of the dot product. It will some small insight about how you can use the dot product in a computer science, or in data structure, I would say mostly. So there are a couple of properties of the dot product. So you can find the list of all of the properties of the dot product in the book. So one of the important one which we would like to discuss here is this property. So essentially, the length of the vector in a square is equal to the dot product of the vector to itself. So in order to prove this, I would like to recall the definition of the length of the vector. So let's say u is a vector with the three components. Let's say it's going to be u1, u2, and u3. And if you remember, the length of the vector u is going to be equal to the first component of the vector in the square plus the second component of the vector in the square plus the third component of the vector in the square. And obviously the norm, or the length of the vector in the square, is going to be equal to the u1 in the square plus u2 in the square plus u3 in the square. Well, at the same time, the u dot to the u is going to be the multiplication of the u1, u2, u3 to itself as a dot product, u1, u2, u3. Well, if you remember the definition of the dot product, we have to multiply the corresponding elements between each other and then sum them. So essentially, the first component here is going to be multiplied to the first component, which is u1 in the square. The second was the second, which is u2 in the square. The third was the third, which is u3 in the square. And if you sum, we are going to obtain essentially the same thing as here. So the u dot u is, it appears, the same as the u norm in the square. Well, the importance of this equation is that later on, whenever we are going to prove some equations about the vectors, we are going to expand the norm of the vector in the square mostly as the u dot u. So we are going to use this equation in order to expand the norm in the square as the u dot u. Well, let's try to do this. So one of the really important theorems about the vectors and the dot product is this equation. Is this equation which involves the angle between the two vectors. So let's say you've got two vectors u and v, and the theta, let's say, is going to be an angle between them. Then the dot product of the u to the v is equal to the length of the u times the length of the v times the cosine of the angle between them. So geometrically, it is going to look like this. So you've got two vectors u and v, and the angle between them theta, and the u dot v is equal to the length of the u times the length of the v times the cosine of the theta. So this equation enables us to find angles between the two vectors, and also this equation enables us to determine so-called perpendicular vectors or the orthogonal vectors. So in order to prove that, we are going to create the triangle. So if you remember, if you just place the two vectors to start from the same point, and then if you just connect their ending points, it is going to be a vector which is obtained by subtracting one of the vectors from the another one. So either u minus v, either v minus u. The only thing is the direction of this black vector is going to depend on whether v is negative or u is negative. Well, in this case, the black vector is going from the v to the u, so that is why v should be negative. So that is why this vector should be u minus v. So the negative v and positive u. So always in subtraction of the two vectors, the resulting vector goes from the negative to the positive. So now we are going to prove this equation using some manipulations from this triangle. And I would like to remind you something which is called the cosines theorem. So if you remember, the cosines theorem involves the lengths of the three sides of this. Well, we are going to try to prove this equation using some equations involving the triangles. So I'm going to use something which is called a cosines theorem. So the cosine theorem, if you remember, involves the length of the three sides of the triangle and one of the angles. So let's assume that the length of this red side is equal to the norm of the u. The length of the blue side is going to be the norm of the v. And the length of the black side is going to be the norm of the u minus v. And if you remember, the cosines theorem is going to tell you that the u, So now we are going to try to prove this equation, and the proof of this equation involves the equations about the triangles, and one of them is so-called cosines theorem. It uses the lengths of the sides of the triangle. The length of the red side is going to be the norm of the u. The length of the blue side is going to be the norm of the v, and the length of the black side is going to be the norm of the u minus v. Right? So, if you remember, the cosines theorem is telling you that the norm of the u minus v in this square, the length of the side which is opposite to this angle theta, is equal to the norm of the u in this square the norm of the v in the square minus the norm of the u, the norm of the v times the cosine of the theta. And if you remember the Pythagoras theorem, which is the particular case of this cosine theorem, where the theta is equal to the pi over 2, and it is really important to us to know that the cosine of pi over 2 is equal to the 0. It's important. Well, this is what does the cosines theorem is telling us, which is true absolutely. So the another equation which I would like to use is this one. So the norm of the u minus v in the square, and I would like to expand this. Well, in order to expand the norm in the square, I'm going to use one of the properties of the vectors which we have just discussed in the previous slides. So if you remember, in the previous slides we discussed this equation, u in this u dot u is the norm of the u in the square, right? So now we've got the similar thing here, but instead of u, you've got u minus v. Well, it doesn't matter how you're going to denote the vectors, right? You can denote them like u minus v as well. Well, using this property is going to be equal to u minus v dot u minus v. And now I'm going to expand the two brackets. It is going to be u dot u minus u dot v minus v dot u plus v dot v. And using the same equation, I find that u dot u, it's the norm of the u in the square, the norm of the u in the square, minus 2u dot v plus the norm of the v in the square. Well, I've got the two equations for the u minus v norm in the square, and since the left-hand sides of these two equations are the same, namely u minus v in the square, so the right-hand side of this equation should be the same as well. So I'm just going to copy the right-hand side of the black equation, which is the norm of the u in the square plus the norm of the v in the square minus the norm of the u, the norm of the v. So I think there should be the 2 as well here. 2 is involved somehow there, sorry. So times is the cosine of the theta. And now I'm just going to copy the right-hand side of the blue equation, which is equal to the norm of the u in the square minus 2u dot v plus the norm of the v in the square. Well, I can see here that this term and this term are going to be cancelled out, and this term and this term are going to be cancelled out. This minus with this minus are going to be cancelled out, and what is left is essentially the norm of the u, the norm of the v, times the cosine of the theta is equal to the u dot v, which is the same equation as which we wanted to prove. Right? So we wanted to prove this equation. Again, you don't need to prove this equation every time whenever you're solving the problems, but it is really important equation, and I wanted you to know that this equation is true and know this elegant and simple proof. Well, let's use this equation in order to find the angle between the two vectors. So let's say you're given two vectors, u and v, and I would like to find the angle. So let's find the norm of the u. First of all, the norm of the u is going to be the squares of the components and the sum. It's going to be 2 in the square, which is 4, plus 2 in the square, which is 4, plus minus 1 in the square, which is 1. And then I have to sum and take the square root, which is going to be equal to the 3, right? Square root of 9, which is 3. The norm of the v is going to be equal to the square of the 5, which is 25, plus the square of the 4, which is 16, plus square root of 2, which is 4. And I'm going to obtain square root of 45. Well, now I also need the u dot v here. So the u dot v is equal to, so I need to now multiply these two vectors component-wise. The first component 2 with the 5, which is going to be equal to the 10, plus the two second components. 2 should be multiplied to the minus 4, which is minus 8. And then the last two components, which is minus 1 times the 2, it's going to be minus 2 or plus minus 2. And if I add all of these items, it is going to be equal to the 0. So now I can just put all of these attributes to the equation to calculate the angle between these two vectors. It is going to be 0 is equal to the 3 times the square root of 45 times the cosine of the theta. It is obvious that I can just divide both of the sides to the 3 times the square root of 15 and obtain that the cosine of the theta is equal to the 0. And if I ask you at which angle the cosine is going to give you 0, you might say me, hey, this is going to be equal to the pi over 2 or 90 degrees. So any vector you can imagine which have the 90 degrees between them are called the orthogonal vectors. So the 90 degrees, right? So the two vectors are called orthogonal. Or speaking simply, they're called perpendicular. Perpendicular. So especially in 2D, we call the two vectors as perpendicular if the angle between them is 90 degrees. But in general, I would call them as orthogonal vectors. So this will bring us to one of the important conclusions about the dot product and the angles between the two vectors. Namely, the two vectors u and v are orthogonal if and only if the dot product is equal to 0. So here, if and only if means that these two statements are going to work in both of the directions. Namely, if two vectors are orthogonal, if u and v are orthogonal, then it implies that u dot v is equal to the 0. And at the same time, if u dot v is equal to the 0, then it implies that u and v are orthogonal. So which is one of the really important conclusions which we can obtain from the dot product. Well, I mean, the proof or the definition, the proof of the statement is really easy or really intuitive, because if you remember, the cosine of the theta is equal to the u dot v divided to the norm of the u and norm of the v, and the cosine of the theta is equal to the 0 when the theta is equal to the pi over 2, and also when the u dot v is equal to the 0. Well, what we have learned today, we've learned about how to find the angle between the two vectors. So essentially, instead of t here should be the dot product here, u dot v divided to the norm of the u times the norm of the v. And at the same time, the two vectors are orthogonal if and only if the dot product is equal to the 0. So this is one of the really cool tools to identify the orthogonality of the two vectors. Well, I hope that this was very helpful for you. Thank you very much for your attention.